In previous videos, we looked at several different addition reactions, which were reactions whereby we added a molecule across the two carbons of a double bond. Now, in this video, what we're going to look at is a very specific reaction called a halogenation reaction. And as the name suggests, halogenation involves adding a halogen to an alkene. Okay, so in general terms, we start off with an alkene and we react that with one of the halogens. Now, there's four different halogens. You have fluorine, bromine, chlorine, iodine. Really, this only works at least well for bromine and chlorine. Okay, so we'll say that X is equal to bromine and chlorine. So definitely not fluorine. Maybe with some success on iodine, but that's about it. Okay, so just like all of the other addition reactions, what's going to happen here is we're going to break the pi bond and form two new sigma bonds. Okay, and then those two new sigma bonds will be to the two carbons, to the two atoms of the halogen that's involved in this reaction. Okay, so just for a couple of examples here, if you consider taking trans 2-butene and reacting that with Br2, okay, what we're going to wind up with is going to look a lot like what we started off with at first. Okay, we break the pi bond between these two carbons, and we have a new bond to bromine on each of these. Okay, and that's our product. Okay, another way that I could have written this time using a cyclic alkene, would be if I just wrote the halogen reagent over top of the arrow. But again, we can draw the product by redrawing the reactant, breaking the pi bond between those two carbons that were part of the double bond, and make two new sigma bonds. Both of them go into chlorine. Okay? And it's just that easy. Now, there are some mechanistic concepts that we need to look at here, because at first glance it doesn't seem like this reaction should work. Okay, so let's dig deeper into the mechanism. Okay, so we know that when we have a double bond, that the electrons in that pi bond make that portion of the molecule very electron rich. And up until now, we've had that electron rich portion attacking something that was really positively charged. But here, that doesn't seem to be the case. Okay, because bromine appears to have a nonpolar covalent bond with another bromine atom here. They have no difference in electronegativity, so how could this possibly be polarized? Well, by itself, it's not really. But when we have the electron-rich alkene come close to it, okay, and start getting near one of these bromines, what's going to happen is the electrons that are on that bromine, okay, are going to be repelled by it. Okay, we say that bromine is polarizable. Okay, and what that means is that bromine has most of its electrons in shells that are very far away from the nucleus. So it's relatively easy to push those electrons around. So when the double bond gets close to one of these bromines, okay, that bromine starts pushing its electrons towards the other bromine, giving us just just enough positive charge on that bromine for the reaction to take place. Okay, so then once the double bond completely attacks, we get a breaking of the bond between the two bromine atoms. Okay, so the product we get, the intermediate that we get is going to look like this. Now I'm just arbitrarily showing the bromine going to the carbon on the left-hand side and forming a carbocation on the right-hand side. And of course, we'll also form bromide. Okay. Now, before I go on to the next step, which is, I'm sure you can imagine, the bromide attacking the carbocation, I do want to mention that this carbocation that forms is stabilized. Okay, and it's stabilized through resonance. You can imagine bromine, being as big as it is, can get its electrons close enough to that carbocation to donate its electrons into that. Okay, which gives us a resonance structure. Where we form this three-membered ring between the two carbons and the bromine. Okay, we call this the bromonium ion. And if we had been talking about chlorine, we would have been talking about the chloronium ion. Okay, and again, this serves to stabilize the intermediate. It should also be noted that the formation of this three-membered ring is actually integral to understanding the stereochemical implications of this reaction. But let's first finish up writing this mechanism. Okay, so we can show the bromonium ion with a positive charge on bromine, reacting with bromide. Now, at this point in time, it's not important to recognize which carbon gets attacked. It will be, but not just yet. So the bromide's going to come in now, and it's going to attack. Okay, and it doesn't matter which carbon at this point. Okay, but the way that this reaction has to happen is kind of like an SN2 reaction, in that in order to attack, it has to be on the opposite face that the other bromide is. Okay, so we can break this bond. Okay, again, this has huge impact on the stereochemical outcome of this reaction. Okay, and then get our product. Okay, so that's how the reaction works. Now, like I said, the stereochemical outcome of the reaction is largely dependent on the nature or of the formation of the bromonium ion. Okay, because the bromonium ion forms, we don't see any syn addition product. Okay, we only get anti-addition. Okay, which means that the two groups that are being added to the carbons of the double bond are being added from opposite faces. Okay, so for example, let's look at what happens if we take cyclopentene and then react that with bromine. Okay, the product that forms has to have the bromines oriented on opposite faces of the ring. Okay, and there's two possibilities there. We can either get this enantiomer or this one here that I'm drawing. Okay, and sometimes there's some confusion as to how these are enantiomers. If you have any questions about that, make a model of it and see me during office hours if you have more questions after that. I want to point out that there is one other possible stereoisomer that could form, and that is the one that has the bromines on the same face, and this does not form. Now, to rationalize what's going on here with the stereochemistry, what I want to do here is look at the mechanism in a little bit more detail. Okay, so we know that the alkene is going to attack the bromine, which is going to produce a bromide and a bromonium ion. Now, I'm going to just draw that bromonium ion right now. So I'm going to start off by drawing the ring. So it's kind of laying on its back. Okay, so that when the bromonium ion forms, okay, it can only form in one of two ways, either on the top face or the bottom face, but because of the symmetry in this molecule, it doesn't matter which face we choose. Okay, so we're going to wind up, oh, by the way, I want to just emphasize these H's here because I'm going to be drawing them here. Okay, and then we have the bromonium ion on the bottom. Okay, so that when the bromide comes into attack, it has two choices. Well, technically more, but let's just look at those two first. We know that it cannot come over here and attack on the same face as the bromine. Okay, the reason why that can't happen is because the bromine's there. The bromine's blocking that. Okay, so the next possibility is to attack on the opposite side. Okay, when that happens, I'll keep this in red here. Okay, we wind up with one bromine going down and one going up. Okay, and that corresponds to this product right here. Okay, alternatively, the bromide could have attacked on this carbon and then broke this bond. And if that were to happen, okay, the product we would have gotten would have looked like this right here. Okay, and that corresponds to that product. Okay, and again, the attack of the bromide on the same face that the bromine's already on cannot happen. Okay, and that's the one that would have led to the one that I'm circling right here. Okay, now very closely related to the halogenation reaction is the formation of a compound called a halohydrin. halohydrins are, you can tell by the name that there's something to do with halogens, there's something to do with hydro, water. Okay, so there's halogens and water being added across a double bond. Okay, so an example, well, actually, just a general form of this reaction involves taking an alkene and reacting that in the presence of elemental halogen. Again, bromine and chlorine are your best bets here. And we do this in the presence of a lot of water. Okay? And what we get as a result is a compound that contains a halogen and a hydroxy group. Okay, so this is called a halohydrin. Okay, and as you can imagine, there's a lot of different halohydrins out there, different substitutions and different halogens and all that. Okay, now let's look at a couple of examples here. Let's go to a cyclic example. And let's have that react with chlorine in water. Okay, just like we did with all the other additions, we start off by redrawing the reactant, identifying those carbons that were part of the double bond, and form two new sigma bonds. Okay, now with the halogenation, both of those would go to chlorine. But because we flooded this reaction with water, before that chloride gets the chance to attack, the water does. Okay, and that's the product we would get. Okay, similarly, if I started with an alkene like this and reacted that with bromine and water, again, we just redraw the compound we started with, identify the carbons that bear the double bond. One of them is going to get a bromine, the other one's going to get a hydroxy. Okay, now how does this work? Well, it functions by the same sort of mechanism that we saw when we were talking about halogenation. It's just a matter of what does the attacking on the carbocation intermediate. Okay, so let's look at this reaction here. And for this example, I'll show it taking place with chlorine. Okay, so just like we saw before, chlorine being more polarizable than some other elements, when the electrons when the electrons from the double bond get close to it, will become slightly polarized. Okay, so as this gets close, this chlorine pushes its electrons over to the other chlorine, takes on a little bit of positive charge, this guy takes on a little bit of negative charge, so that the attack can then take place and the electrons are thrown onto the other chlorine. Okay, now again we're going to form a halonium ion, so this particular one's going to be a chloronium ion. Okay, and then we form chloride as well. Now, in principle, the chloride could come back in and attack and give us just the addition of chlorine across the two carbons. The problem is, remember, that the chlorine is going to wind up having to go around to the other side of the molecule in order to do its attack. And if we have enough water present, there's a very good chance that a molecule of water will find that carbon before the chloride does. Okay, so the next step okay, is for a molecule of water to come in and attack the carbon. Now again, this could have been either one of the carbons. Let's not worry about which one just yet. And that'll push the electrons up onto the chlorine. Okay, so chlorine winds up here. And we wind up with water down here. Okay, so then the last step of the reaction is for another molecule of water to come in. And remember, we said that there was a ton of water in here, so there's no shortage of water molecules come in as a base. And pluck off that H and push the electrons back onto the oxygen. And what we wind up with is our chlorohydrin product. Okay, now the question becomes, what happens when we have to deal with regiochemistry? In other words, what would happen if we were to start off with one of my favorite unsymmetrical, or I should say non-symmetrical alkenes? Okay, so we start off here with a alkene that has hydrogens on one side and methyl groups on the other side. Okay, and we submit this to the conditions for hydrohalogenation. Sorry, not hydrohalogenation, halohydrin formation. Okay, and we know that when we're trying to figure out what the product is, we just kind of redraw our starting material. Okay, but this time we have two new pi bonds. So one carbon will have the two CH3s, one will have the two H's. And we know that at the end of the day, one of these carbons gets a bromine and one of them gets a hydroxy group. Okay, so I'm going to just arbitrarily put the hydroxy group on the left-hand side and the bromine on the right-hand side. Okay, now the other possibility would be having the hydroxy group and the bromine flipped. No bromine there. Okay, so in principle, these are two products that could form, but they don't both form. In fact, the product that's on the right-hand side does not form. Now, when we saw this before, we were able to call upon Markovnikov's rule. But Markovnikov's rule dealt with carbocation stability and having hydrogens going to the less substituted. There's no hydrogens here, okay? And there is no outright single carbocation. Okay, remember, we're going to have a chloronium or bromonium ion. Okay, so we need to look at this mechanism a little bit more closely. Okay, so remember, the first step here is going to be the formation of the bromonium ion. Okay, I'm not going to draw the arrows, I'll just draw the intermediate itself. Okay, so here we have our bromonium ion. Okay, and we have our two CH3s on the left side and our two H's on the right side. Okay, so the answer, or the question is, where will water attack? Okay, and to answer that question, we kind of need to do a flashback to when we talked about the addition reaction to epoxides. So I'm just going to kind of make a little box off to the side here, just to remind you of what I'm talking about. If you don't remember this, please make sure you go back and take a look at this section of the textbook. Let's see here if I can find the page for you real quick. Let's see. If you look at, I think it's section 9.7. No, not 9.7. Okay, sorry, that's 9.16, 9.16. Okay, and we said that when we had very strong nucleophiles, that the attack that would take place on the epoxide okay, would occur on the side that was less substituted. Okay, so let me just actually draw that out a little differently here. Let's say we do it like this. Okay, so if we have a strong nucleophile, the attack would take place on the less substituted side. Now, if we had a weak nucleophile, we knew that the attack could not take place without catalyzing the reaction with a strong acid, which would protonate the epoxide. Okay, and protonating that epoxide there would actually weaken this bond right here. It would even make these carbons that are in this region here be more planar, so that the weak nucleophile could attack. So the attack would take place on the more substituted carbon. Okay, so what do we have here? Well, here we have the bromine positively charged. Kind of looks like that epoxide with its positive charge. Okay, we have a weak nucleophile. Okay, so we would expect then for it to behave like the bottom case with the epoxides, which means we get the attack on the more substituted side, breaking the bond between carbon and bromine. Okay, and that takes us to the product that we get. Okay, so it does make sense. We just kind of got to work our way through the mechanism.